If you read the technology press lately, you'd think the only thing that matters in quantum computing is the size of the gas tank. Headlines constantly brag about new processor chips hitting 100, 500, or even 1,000 qubits. But judging a quantum machine by raw volume is mostly a vanity metric. A massive physical qubit count is useless if the system suffers from decoherence. Decoherence is the process where a quantum particle loses its fragile state the second a stray vibration or temperature fluctuation hits it. If the qubits vibrate out of alignment before a calculation can finish, the whole system just outputs noise. That is why the engineers actually building these machines stopped chasing raw volume. The real milestone is something called gate fidelity. Specifically, the industry is racing to achieve the 4 nines, a 99.99% operational accuracy rate, meaning a system can perform 10,000 operations before a statistical error is likely to occur. Hitting that accuracy threshold officially closed the door on the NISQ era. NISQ stands for Noisy Intermediate Scale Quantum, a period where machines were real but too glitchy for practical, sustained use. Now, by grouping enough of these highly accurate physical parts together, labs are creating stable, self-healing, logical qubits that can catch and fix their own errors on the fly. This chart shows exactly why building a self-healing quantum system was so difficult. Look at the processing style and limitation rows. Classical computers are strictly deterministic, moving step by step through rigid ones and zeros, limited only by how many transistors we can cram onto a chip. Quantum computers process information probabilistically and in waves, making them incredibly powerful but completely fragile. Crossing this fidelity threshold pushed the hardware from a delicate physics experiment into a working tool. We call this the utility threshold. Quantum computers are now solving highly specific, highly valuable mathematical problems that classical supercomputers simply cannot process. To keep those qubits stable enough to hit the utility threshold, the hardware has to live in extreme isolation. These machines depend on massive dilution refrigerators, heavily guarded vacuum chambers designed to freeze the quantum chips to temperatures colder than deep space. You can't exactly fit one of those on a desk, but through Quantum as a Service, or QaaS, you don't have to. QaaS is a cloud computing model where companies like IBM, AWS, and Azure host the physical hardware in their own labs, allowing anyone with an internet connection to rent time on the machines. Because of that cloud access, the people running the experiments look entirely different today. You no longer need a PhD in physics to manually tune microwave pulses in a cryolab. Instead, a new generation of software developers is writing scripts using standard open-source libraries, sending commands over the internet straight to the quantum core. By democratizing access to the hardware, the industry exposed its actual bottleneck. The major constraint slowing down quantum development today isn't the physical chips. It is a global shortage of quantum-native developers who actually know how to code in a probabilistic environment. Even with all this cloud access, quantum computers will never replace your laptop or even standard server farms. They aren't general-purpose machines built to run operating systems or host websites. This diagram outlines how a classical computer domain interacts with a quantum domain. Think of the classical computer on the left as a film director and the quantum processor on the right as a highly specialized visual effects team. The classical system sets up the problem, manages the inputs, and controls the overall workflow. When the classical director hits a wall of exponential complexity, it tags in the quantum VFX team. The quantum processor handles the massive mathematical lifting, sends the output back, and the classical machine updates the parameters. They iterate in a continuous loop until they find the optimal solution. We aren't waiting for a standalone quantum era where classical logic is discarded. Instead, organizations are actively augmenting their existing systems with highly specialized quantum coprocessors built to solve specific roadblocks. One of the most immediate roadblocks these coprocessors are breaking is in chemistry. When classical computers try to design a new drug molecule, they have to rely on mathematical approximations. They are essentially forced to guess how electrons will behave, and those approximations fail as molecules get larger. Quantum processors naturally operate using the exact same wave mechanics that govern atomic structures. Because they speak the native language of electrons, they can simulate complex molecular interactions and chemical reactions thousands of times faster than our best supercomputers. That same ability to hold massive amounts of variables at once is also being deployed to untangle the global supply chain. If you ask a classical computer to find the most efficient route through an entire logistics network, it has to test each individual path sequentially. A quantum optimization algorithm explores the entire maze of variables simultaneously, calculating weather, fuel costs, and crane schedules all at once to find the single most efficient outcome. In pharmaceutical labs and massive shipping ports, quantum utility is already active. It has moved out of the whiteboard phase and is actively breaking the hardest bottlenecks in modern industry, and that utility is expanding. Financial institutions are running pilot programs to optimize real-time risk across thousands of variables, and researchers are using quantum layers to efficiently sample the massive, unstructured datasets required to train artificial intelligence models. For decades, our entire digital infrastructure has operated like a flashlight in a massive cave. It is highly effective, but it can only illuminate a tiny fraction of the possible paths at any given moment, constrained by linear, step-by-step logic. A functional quantum computer operates like a sonar ping. It utilizes superposition and entanglement to map the entire space instantly, seeing the whole structure of a problem before collapsing into a single, highly probable answer. For most of human history, the bizarre rules of quantum mechanics were treated as an obstacle to engineering. Now, by choosing to build with those very same rules, we are treating the underlying mechanics of the universe as our ultimate computational advantage.